All right. So here we are. Let's get started. So we're going to go back now. We just started talking about imaginary numbers, as a matter of fact. So that was chapter 3. But actually, before we do that, we have a problem set. I almost forgot. We have a problem set to go over, don't we? Yes, let's get that going first. And then we can look at chapter 3. All right. So let's let me open that up. Chapter 2 problem set. All right, so this is pretty straightforward. These are all linear functions. Let's just get that rolling. Today's the 3rd. All right, and then when this is done, we can get back to chapter 3, where we had just barely started introducing imaginary numbers, which are actually a lot more interesting than you might think. We're actually going to see some interesting videos which talk about what it is, what they are, and how they were developed. And for a lot of historical reasons, they're also very interesting in the development of mathematics. Anyway, so let's take a look at these. So first, we're going to find the slope of the line that passes through these 2 points. So what is this all about? Well, you might recall that the slope of a line is formally defined as y. Let's write it up here somewhere. The slope can be thought of as delta y over delta x, or we could simply think of that as y2 minus y1 over x2 minus x1. So in each of these cases, what we can do is think of the first pair as x1, y1, and the second pair as x2, y2. So this is x1, this is y1, x2, y2. So if that's the case, then the slope would be, since it's y2 minus y1 over x2 minus x2 minus x1, we'll have 10 minus 4 over 4 minus 2, 6 over 2, or just 3. And it's really that simple. Okay, so these are all the same types of problems. These are all slopes. So they're all done in exactly the same way. All right, now how about this one? And we don't have to write out the formula every single time. This would be 11 minus 5 over 4 minus 1. Okay, so 6 over 3, which is just 2. Okay, so these are very straightforward, as you can see. We just have to be careful with the negatives, that's all. The one thing that can always trip us up is negatives. All right, so here again, y2 is, we have 2 minus 4 divided by 5 minus 1. Okay. So we're going to have minus 2 over 6, which is minus 1/3. Very nice. All right, now what about this next one? So here the slope would be, so we have 6 minus 2, 4 minus 8. So 8 over minus 4, which is, of course, minus 2. All right, and then finally, we got one more. That would be 3 minus 11 over minus 4 minus 6, okay? So that leaves us with minus 8 over minus 10, which reduces to 4/5. All right, well, those are pretty straightforward. So now in the next batch, though, what we're being asked to do is not just come up with the slope, but the entire line. All right, so of course, there's different ways of doing this. And so in each case, we might have to try a slightly different approach. But recall, of course, that the equation of a straight line can be written in a couple of different ways. We can use, for example, y equals mx plus b. Or another alternative is to write y minus y1 equals m times x minus x1. So the one you would use, it really just depends on what information you have. Now here we've got f of -5 is -4. So just keep in mind that f of whatever, f of x is just y. So what do we do with this one? Okay, well, the first thing we always want to do is get the slope. So the slope is y2, of course. All right, so we can think of this as y2. Sorry, that's not y2. This is y2. This is x2. Okay, the number we're plugging in here is x2. This is y1, and this is therefore x1. So that was the only thing you had to watch out for, getting those lined up properly. So we'll have 2 minus a minus 4 over 5 minus minus 5. Okay, and that's going to leave us with 2 plus 4, which is 6, divided by 5 plus 5, which is 10. And so the slope is 3/5. But now this time, we'd like to also come up with the entire equation of that straight line. So because we have a slope and 2 points, we actually can go a couple of different directions, but let's try it this way. All right, so in other words, we'll have y minus, now remember, y1 is defined as -4. Here we have 3/5 x minus minus 5. And again, you can see the only real challenge here is taking care of with all those negatives. So we'll have y plus 4 equals 3/5 times x plus 5. And when you multiply this out, you'll have 3/5 x plus 3. 3/5 times 5 is just 3. Now all I have to do is subtract that 4 from both sides. And I'm done. Okay, so here it is. That's the entire equation. Nice. Now we could have used y equals mx plus b just as easily. It doesn't really matter unless it specifically asks you to use one or the other. You might recall this is the point slope form. And this is sometimes called slope intercept form. And that's just because of what information you have in this equation. All right, now how about number 7? Now it's a very similar type of problem. Okay, but again, the challenge here is recognizing that y, this is y1, 2 rather, this is x2, y1, and x1. Okay, so the equation of slope never changes. So we have 1. Oh, yes, go ahead.
Like, I can remember why those are y, or I can remember that those are y2 and y1 and stuff, but I don't really get why they are y2 and y1 and x2 and x1.
Okay, because, well, the 1 and the 2 part are completely arbitrary. Either one could be 1, either one could be 2. But because it says f of x, if you start out by saying, this one is telling me that f of x is 4, evaluated when x is 1. So basically what this is saying is that when x equals 1, no, minus 1 rather, f of x, which is also equal to y, equals 4. So it's just another way of writing that we have. See, down here, they're written as ordered pairs. This is the same thing as saying that the point -1, 4 is on the line. Okay, so in other words, it's just a fancy way, I guess we could say, of saying the same thing.
Thank you.
Okay. All right. Anyway, so then we have 1 minus 4 over 5 minus -1, which is -3 over +6, which is -1/2. And once we have that in place, we can use either approach to find the equation of the line. So we can try y minus y1 equals m times x minus x1. Okay. So remember, y1 was 4. And x1 is -1. All right, so we're almost there. Y minus 4 equals -1/2 of x plus 1. Again, got to be so careful with those negatives. Now here, what I'm going to do, I'm going to add this 4 to both sides, but before I do that, I want to rewrite it as 8/2. So we'll add 8/2 to both sides. And this will become plus 7/2, and I'm done. All right, now these next two, we just have the 2 points. All right, so that means it's a little bit more straightforward, I think. You can think of this now, you can identify this very easily as x1, y1, x2, y2. (10 minus 4 over 4 minus 2). That would be 6/2, which is 3. All right, now once we have the slope, and again, we can try this equation. So we'll have y minus 4 equals 3 times x minus 2. And then we just can rearrange this algebraically a little bit. All right, now all I have to do is add this 4 to both sides. And we're done. Very good. All right, now the next one is exactly the same. It just gives us the 2 points. And let's see what we can do with that. Okay, right here. So we can think of this as x1 and y1, x2 and y2. The slope is y2 minus y1, x2 minus x1, 11 minus 5, 4 minus 1 is 6/3, which is 2. Okay, so the slope is 2. And now we can go back to our point slope form. And let's see what we can do with it. Okay. Oh, it's determined to make us look at the weather, isn't it? That's the annoying part. I don't mind the pop-ups, but when it sort of forces you over to that website, that's pretty annoying. But anyway, so we have y minus 5 was 2 times x minus 1. And so let's see what we can do here. 2x minus 2, and then I add the 5 to both sides. 2x plus 3. All right, now there's one more. Now this one looks a little bit different, but it really isn't. They're just telling us the 2 points. It just so happens that the 2 points they're giving us are the x and y intercepts. It doesn't change anything though. We can still think of this as x1, y1, x2, and y2. All right, so let's do this. Okay, minus 3 minus 0 over 0 minus 2. All right, so that turns out to be positive 3/2. And then, with that knowledge in place, let's see what we've got. So we got y minus 0 equals 3/2, x minus 2. And you're done. That's it. That 0 there is very helpful, that's for sure. So therefore, that's our final result. All right, so that was pretty straightforward. Now, what's coming next is just a reminder. We need to know when lines are parallel and when they're perpendicular. So what we have to be able to do is basically write these equations in such a way that we can see their slopes directly. So in other words, if they're algebraically not in the form y equals mx plus b, we have to rearrange them to make sure that they are. It's the only way we can tell. All right, so for example, let's look at these two. Now, they're not written out in a nice form, are they? No, they're not. That would be too easy. So we have to do it ourselves. So let's try this first one. So our goal is to rewrite these, rewrite them in the form y equals mx plus b. So we're just going to do a little rearranging algebraically. I'll subtract the 4x from both sides, and then I'll divide out by that -7. Actually, let me do one more thing here. So if I divide out with this -7, what I'll end up with is y equals positive 4/7 x minus 10/7. That's the first equation. Now we need to do the same thing for the second equation. So therefore, first get the x on the right-hand side. And we divide out the 4 from both sides. And we're going to end up with y equals 1/4 minus 7. Oh, actually, you know what we should probably do? Let me go back for a second. And not that it really matters, but I'd rather have the x come first. Let's subtract. Let's write it like this. That's better. I've subtracted the 7x. Now when I divide out that 4, yeah, it'll be lined up just right. Y equals -7/4 x plus 1/4. Now, what are we looking for here? We're looking at the two slopes. That's really all that matters. All right, we have -7/4, positive 4/7. And what you'll notice is that if I multiply the slopes together, it ends up being -1. And that means, of course, that the lines are perpendicular. Okay, because that's what it means to be perpendicular. Their product of their slopes is -1. And then what that means is that wherever they cross, they're crossing at right angles. All right, so whatever they look like, where they cross, we have a right angle. And that's what the word perpendicular actually means. So in other words, something like this. -1, oh, because this is, all right, let me write it out. I'll go through one more step. This is actually -28/28. Okay, if you multiply the numerators and the denominators, you'll get -28/28, which is -1. So I don't know exactly what they look like, but they're going to cross at a right angle. You're welcome.
I don't.
Go ahead.
So for each one of these, do we multiply the slopes together? Is that like?
No, you don't have to. If the slopes are equal, instead, then the lines are parallel. So you don't have to do that.
So like, why did you? Like, could you?
Oh, I
do
think just,
they're perpendicular without doing that?
yeah, you could see. I mean, one is, you could also think of them as being inverses with the negative sign. But just to prove it, just when you look at it, you should be clear that they're perpendicular rather, because basically think of them as inverses plus the negative sign. But the formal definition is when their product is -1.
Gotcha.
All right, but if they're not, now if you notice that they're equal to each other, then they're just parallel. You don't have to do any multiplication.
Yeah.
Now, if the slopes are not equal and their product is not -1, well, then you just conclude the lines are neither perpendicular nor parallel. Okay, so if you look at the question, that it allows for that possibility. Okay, in other words, if you read it up here, you notice how it's saying determine whether they're parallel, perpendicular, or neither. So we have to be prepared for the possibility that some of these at least don't fall into either category. But if you do multiply them out and get -1, then they're perpendicular. All right. All right, so it's the same strategy for all of them. There's nothing new over here. We just have to be careful, as usual, with the negatives. So if we have 3y plus x equals 12, we want to get rid of this x. And then we'll divide out by 3. So ultimately, we have negative x over 3, or let's write it as -1/3 x plus 4. And again, we don't really care about the intercept. What matters to us is the slope. So for the second one, now the second one is almost already in the right form. We just need to multiply both sides by -1. And you can see, you can multiply these together, you'll definitely not get -1. And they're certainly not equal to each other. Okay, so since the product of the slopes is not -1, and the slopes are not equal, this means that the lines are neither perpendicular nor parallel. Okay, and that's all you had to say. And most lines, let's face it, are not going to be either or. In fact, it's kind of rare that they do fall into one of these categories. If you look at all the potential lines out there, the vast majority of them would not fall into either category. All right, so how about these two? And you can't really tell just by looking at them. I mean, unless you do this all the time. You have to go through the formality of rearranging them All right, let's get that 3 out of there by dividing both sides. All right, so that's the first one. The second one, I'll move it over here. Now this one, all I had to do is divide out that -6. Ooh, look what's happening here. Y equals -8/6x minus 1/6. But this is just the same thing as -4/3 x minus 1/6. So the slopes, look at that. They're the same. So that means for the first time, so since the slopes are equal, the lines are parallel. Okay, so all right, so so far we've got one of each case. We've got a perpendicular set of lines, parallel, and neither. Very good. All right, so let's see what's coming up next. All right, what do we have now? So for this pair, let's see what we can do with it. 6x minus 9y equals 10. All right, I'm going to subtract this 6x from both sides. Divide out the -9. So y equals, now here the ratio of -6 to -9 is actually 2/3. And then here I have -10/9. Again, we're not too concerned with the intercept. The second line, okay, subtract that 3x, divide out the 2. Oh, look, we might be in luck this time. Why do I say that? Because if you look at these carefully, you'll see that the product of these slopes is -1. Let's look at it. All right, -3/2. 2/3, which is -6/6. And we have a winner. So therefore, in this case, we conclude that since the product of the slopes is -1, the lines are perpendicular. Nice. Okay. And then there's one more. All right. Now, oh my God, this first one is already done. That was easy. Now this one, well, that doesn't happen very often, does it? Something just automatically appears in the right form. Yeah, not likely, but all right, today we got lucky. So I'll divide out that 2. Oh, I think we have another winner here. Because if you look at these slopes, we've got a 2/3, and in fact, it's even the same ones, isn't it? But that was just a ridiculous coincidence. It wasn't planned that way, that's for sure. So since the slope, oh, sorry, let's write that out formally. The product of the slopes, yeah, more perpendicular. Yeah, look at that.
Hey, Professor,
Yes.
I just got a quick question.
Sure, go ahead.
In terms of like the like I get that if the product of the slopes is -1, it's perpendicular, but does the y-intercept, like, is that anything that like we should consider here?
No,
Or
yeah,
not
I'll tell
really?
you why.
Yeah.
Because what's going to happen is that we know that they have to cross at one place. Now, the y-intercepts will determine exactly where they cross. But for this question, at least, all we need to know is the fact that they're perpendicular. Okay, so in other words, you might get something like this. In another case, you might get something like this. So yeah, the intercepts will help us figure out where they cross, but for our purposes here, we don't really need to know that. Just do they cross or not
Okay, cool. Thanks, Professor.
at a right angle? Yes, exactly. So yeah, I know you might wonder what are we doing? Why are we ignoring these guys up here? For just to determine if they're perpendicular, we don't need them, but we do know that they will cross at a right angle, and those intercepts will determine exactly where that happens. Okay, so that's why we would need those. If you wanted to say, listen, where do they cross? That's a different matter altogether. In fact, if you're dying to know where they cross, let's just finish this up for a second, and I'll show that to you. So therefore, the lines are perpendicular. And so if you want to know where they're crossing, the exact location, what you could do is say, all right, well, we know that they have to cross somewhere. So let's do this. Let's see, let's write them out again. Y equals -3/2 x plus 1, and y equals 2/3 x plus 1. Well, why don't we do this? Why don't we just set them equal to each other? Whoops, that would help if I had the x there. And then let's see, what do we do now? We've got to consolidate these x's somehow. Let's turn these into sixths. Okay, 9/6 x. And well, we don't. All right, we'll turn everything into sixths. How about that? 4/6 x plus 6/6. So what I'm going to do is add this to both sides, giving me 10/6 x and then I can subtract these 6/6 from both sides, which leaves me with -3/6 is 10/6 x. Now I'm going to multiply both sides by 6 to come out with -3 equals 10x. And then I'll divide both sides by that 10. So where they cross, x is equal to -3/10. So I can obtain the y from either of the two equations because it has to be the same. So let's just pick this one on the right. And that means that I've got y equals 2/3 times -3/10 plus 1 minus 6/30 plus 1. And that, of course, can be reduced to -1/5 plus 1. So that means that y equals 4/5. So they cross at the point of -3/10, comma 4/5. Now, what we can do here is, if you want to visualize this, I can just open up Excel and throw this in there real fast. I think it's a good idea that we can see what's actually happening here. Now, keep in mind, Excel is not the best graphics package in the world, but we should be able to come up with something reasonable. So let's see, what do we have here again? So we've got these two. Make this a little bigger. And over here we have y equals 2/3 x plus 1. All right. So what I'm going to do is create a chart that I'm hoping will show what we're looking for. And let's call this y. Let's call this y1 and y2. How about that? So we can tell them apart on the graph. So we'll start with, let's say, -10, -9, and we'll go all the way down to +10. I want to make sure that the graph that I'm choosing will actually cover the points where they overlap or they cross. All right. So now I'm going to fill in the formulas. y1 okay. And then y2 is 2/3 times this number plus 1. Oh, I screwed it up. This is 1/2. That's better. All right. I had the wrong formula for a second there. Let's see. All right. Let me just double check. -3/2 of this plus 1/2. Good. Over here, I have 2/3 of this plus 1. All right. So what I'm going to try to do now is graph this. I'm hoping that it will look reasonable. You can actually see what they look like. It's only giving me 1. That's interesting. All right, now hold on. Well, all right. It's really, you know what, let me do this. Let me change the numbers that I'm looking at. It looks like I want to get in really close here. So let's change the range of values. Let's try -5, -4, let's say. I'm trying to make the chart look as clear as I can. All right, let's try it again. Well, it's trying. You know what? Let me try it one more time. It's really crude, but I think if I adjust these numbers properly, yeah. Let's just get rid of these. That should do it. Man, this is tough. This is tough to do properly. This is where they're crossing. I mean, but wow, that's. But I mean, it just, if you come right in on this point here, where did we predict that it would cross? We're looking at, yeah, I don't know about this. I think I know what the problem is here. Let me just check something out. I have a feeling that I know what the problem is. It's not showing the values of x properly. All right, let me try it one more time. I think we'll be able to get it just right. All right, I think all right, I'm getting it. It's almost there. I just have to I had to make a few tweaks to it. So I really would like to focus on the range where they cross. And all right, hold on one more second. All right, let's try that again. I think this time it'll work. Okay, so now it's labeled properly, and you can see, so the last piece of business is to make sure that the x-axis is actually labeled properly, which at the moment it is not. All right. So now you can see the negative. So let's zoom in on this part. I don't know if this is capable of doing that. Right about here where they cross. So we predicted that it would be 4/5. You see what I mean? It's hard to be sure. It's such a clumsy graph. And that could be, I guess that could be 4/5. And -3/10. You know what? The only way this is going to work is if I choose the numbers a little differently. Let's do this. Let's go for -2, -1.8. You know, really get in really tight on these numbers. Yeah. But then I don't really need so many of them. Let's get rid of these guys. All right, don't worry. We're almost done with this nightmare. All right. Let's give it one more chance. I want it to be like really visible. I guess that's a bit of an improvement. And then we'll fix the axis. All right, well, it's a little better now. Boy. It still doesn't look right. I'll tell you what, I don't want to waste your time with this crap. The graphing in Excel is just not very good. So I'll try to sit down and draw it one that really looks right. But you can find where they cross by setting them equal to each other. And then you'll know the exact location. But the only way you can tell that they're perpendicular is to look at their slopes. But yeah, I mean, there are so many excellent packages out there for graphs. This one is just very, very rough. And I wouldn't rely on this, especially for a math class. It's just not good enough. But all right, well, I'll try to come up with something better for next time. Anyway, so let's get back to this. So then what was next was, oh, here we go. So here we have to find the intercepts. So how do you do that? Now, remember what that means. This is the x-intercept. And of course, at that point, x is 0. Y is 0. We'll call it, I guess, just 0, x. And over here, this is the y-intercept. And at that point, x is 0. Oh, I still wrote this wrong, didn't I? No, I didn't. Y is 0 here. Here, x equals 0. So the point will be, oh, I know what happened. I wrote this part backwards. That's why it's off. It's some value of x combined with a y of 0. Now it's good. This one then would be 0, comma x. That's better. 0, comma y. I keep doing that. There we go. Now it's right. Okay. So the y-intercept means x equals 0, and therefore the point looks like this. X-intercept means y equals 0, and therefore the point looks like this. But the question is, how do we find these? Well, in a case like this, if you rewrite this as y equals negative x plus 2, we already know that this is the y-intercept. Okay, so in other words, when you write out an equation in this form, you've already got your intercept right here. So on this xy coordinate system, this is the point 0, comma 2. What about this one? What about the x-intercept? To get that one, what you actually have to do is simply set this equation equal to 0. So set the equation equal to 0. Because remember, f of x is y, and at the x-intercept, y equals 0. So what we're going to do is just say, all right, well, 0 equals minus x plus 2. I'm going to add x to both sides. X equals 2 is the intercept. The actual point at which this happens would be 2, comma 0. Okay, so you've got two intercepts. Now, of course, you can see this is a very simple case. This is simply minus x plus 2. It has a slope of negative 1. And according to what we just finished, we have a vertical intercept of 0, comma 2, and a x-intercept of 2, comma 0. And that's all we had to do. Now, to find the points, you don't have to draw this picture. All you had to do, in fact, you don't even need the point. That's understood that the y-intercept is the point 0, comma, whatever you found here. So the actual answers that you need just to, answer the question is that the y-intercept is 2, and the x-intercept, by coincidence, is also 2. All right, this is all you really need right here. The rest is, optional. It's icing on the cake, I guess you could say. All right, so it's pretty straightforward. I mean, again, it's a two-step process. Once again, let's go through this again. In order to find the y-intercept, write the equation in the slope intercept form, y equals mx plus b, and the b is your y-intercept. To find the x-intercept, set the equation equal to 0 and find the value of x. That's all you have to do. All right, I want to be consistent here. I'm going to make them either all upper or lowercase x's. All right, so these are very straightforward. All right, let's try the next one. Now, no matter what it says on the left, g of x, f of x, h of x, it doesn't matter. It's still y. All right, so the y-intercept here, and here we got lucky again. It's already in the proper format. It's just 4. Oh man, how lucky can you get? All right, so what about x? So we'll set this equal to a 0. Zero equals 2x plus 4. And minus 4 equals 2x. Subtract from both sides, divide out the 2. And we'll end up with minus 2 equals x. So we conclude that the x-intercept is minus 2. So these are the two halves of our answer. All right. Man, if only all of them were like this. All right. Now 18, again, it's already been written out in the proper format, so we can just go ahead and conclude that the y-intercept is -5. That's done. And then to find the x-intercept, set h of x equal to 0. 0 equals 3x minus 5. Add 5 to both sides. And then we divide out the 3. Oops. Okay, and so therefore our x-intercept is 5/3. All right. Actually, the next one is in the proper form too. Man, this is our lucky day, isn't it? Doesn't usually work out that way, does it? No. All right, let's take a look at the next one. So again, we've already got our intercept. Now for the x-intercept, set k of x equal to 0 and solve for x. Okay, so let me add 5x to both sides and divide out by that 5. So therefore, we say that the x-intercept equals 1/5. And that's the end of that one. Now, the last one you can see is not in the proper form. We'll have to do something about that one. All right, but so far, that's the only one. Yes, that's precisely what we're going to do. We have to move that to the other side. So the first step will be, that's right, it's precisely what we're going to do. So we'll add the 2x to both sides. And then we need to reduce this to just plain y, so we'll divide by that 5. And then we'll end up with what we're looking for, y equals 2/5 x plus 4. But now we still have to set it equal to 0. Solve for x. All right. So 0 equals 2/5 x, 2/5 x plus 4. And now subtract, of course, the 4 from both sides. And now I'm going to have to divide both sides. Now, this is where it can get a little awkward. I'm going to divide both sides by -2/5. And
Yes,
so
sir.
just have, yes, go ahead.
Just a quick question. Would that be the same as like multiplying both sides by like 5/2? Is that like the
Negative
same
5
thing?
over 2. Yes, it would, as a matter of fact.
Okay, cool.
We can do that instead if you want to.
I know, I just want to double check like if
Oh,
that was
no,
the
you
same
were
thing, yeah.
absolutely right. It is the same
Okay.
thing. In fact, we're going to see it in a minute anyway, because what's going to happen here is 4 over minus 2/5 is algebraically the same thing as 4 times the inverse, which is minus 5/2. And so we're going to wind up with minus 20/2 or minus 10. So the x-intercept, so if you had multiplied both sides by minus 5/2 up here, you would have gotten the same result. So dividing by negative, I'll just make a note here, dividing by negative 2/5 and multiplying, quite as you quite correctly pointed out, by its inverse, which is minus 5/2, give the same result. It might have been a little cleaner to multiply both sides by negative 5/2, but we'll end up with the same result anyway. And so x is negative 10. And so therefore, of course, that our conclusion is that the x-intercept is negative 10. All right. So we already had way at the beginning. Oh, you know what we forgot to do? Yeah, we forgot to specifically say that the y-intercept is 4 because we had to rewrite it to find it. Y-intercept is 4. And then we rearranged it. We solved for set y equals 0 and solved for x to get the x-intercept. Very good. Okay. Now for the next part, it looks like something we've already seen, but that's okay. It's just arranged a little differently. And what would that be? Finding whether the lines, oh, there we go again. Parallel, perpendicular, or neither. So here, what we're after, though, is a slightly different approach to doing this. We only need to find the slopes. Okay, we've got 2 lines, we've got 2 points. We don't really need to worry about the intercepts. So what we're going to do is calculate the slopes of these 2 lines like we did earlier, and then compare them to each other to determine if they're parallel, perpendicular, or neither. So again, let's think of this as x1, x2, y1, x2, and y2. So the slope would be the usual. So we'll have minus 24 minus 6 over 3 minus 0. So again, watch out for those negatives. So the first line has a slope of negative 10. What about this second line? Oh, let's come down here. The slope, y2 minus y1. x2 minus x1. So we're going to have minus 71 minus a minus 1 over 8. Oh, wait, what did I do? No, sorry, my fault. I copied the wrong one. Sorry. Let's try that again. Minus 71 minus 19. That's better. 8 minus a minus 1. Okay, because this is, of course, y2. This is y1. This is x2. This is x1. All right, so yes, you can see it's easy to mess this up if you're not careful. So here we have minus 90. And here we have plus 9. There you go. So they have the same slope. So since the lines have the same slope, they are parallel. All right. Very nice. And that's all you need to worry about. We don't need to know. We could figure out the intercepts. We just don't need them for this problem. And you never, that's kind of a rule of thumb in life. Don't do more work than is absolutely necessary. I mean, sure, you can if you want to, but it's not necessary here. All right, and they're all the same. This whole batch of questions, they're exactly the same. We're going to calculate just the slopes and compare them to each other. All right, I don't know, it's good practice. I know it's a lot of repetition, but it's excellent practice. All right, let's try this one. So that means we have 89 minus a minus 55 over 10 minus a minus 8. So this is 89 plus 55. Ooh, let's see what that is. 89 plus 55 is equal to 144. Oh, this doesn't look good, does it? Oh, well, guess what? It doesn't look promising, but it turns out that this is just 8. I never would have guessed. But that's just 8. How do you like that? Oh, well, all right. So now we need the next one. So you never know. When you look at some of these ratios. Now, how about this one? So as usual, the slope, y2 minus y1 over x2 minus x1. So we have minus 14 minus a minus 44 over 4 minus 9. Okay, so what do we have here? Oh, this one looks pretty good. All right, so this is one of those neither cases, of course. Since the slopes are not, do not have a product. Well, first, they are not equal, and they do not have a product of -1. They are neither parallel nor perpendicular. All right. Now, 23. Let's see what that's all about. Here we go. So the slope is all right, here we go. -1 minus 3 over 4 minus 2. All right, well, that was pretty easy. And how about the next one? So we have slope equals 5 minus 3 over 8 minus 6. Oh, this is 1. Okay, well, looks like we're back into the neither territory. All right. Let's see. So since the slopes are not equal and their product is not -1, the lines are neither parallel nor perpendicular. Okay, so that's another no for us. We had one so far, but we have two no's. All right, let's see what's going on down here. Okay, so for this one, the slope okay, so we have 5 minus 7 over 5 minus 1. And then down here we have slope. One minus 3 over 1 minus 1. 4 over 2. All right, so is that right? No, I did something wrong. What's wrong with me? 4 halves is 2. I just wrote it wrong. Sorry. I got it all. I somehow screwed that one up royally. Here it is. The 4 halves is obviously 2. Now we're good. All right. So therefore, now you see what happened here. The product of the slopes is what we were looking for. Is minus 1/2 times 2 -1. There you go. Look, we found what we were looking for. Well, not really. I mean, we don't really care which one it is, but we do recognize that since the products of the slopes, the product of the slopes is -1, the lines are perpendicular. Beautiful. It looks like, I think there's one more. All right, let's do that. So let's try this one. Slope equals -3 minus 5 over 3 minus 0. -2 over 3, and we're done. All right, now what about this one? Oops, oh, what happened there? All right, so let's fill in those numbers. So we got -2 minus a -5 over 3 minus 1. -2 plus 5 over 2, 3 halves. All right, so we have up here -2/3. Ah, look at that. Down here we have 3 halves. So the product of the slopes is, of course, -2/3 times 3 halves, which is -6 over 6, which is, of course, -1. And so our conclusion is that since the product of the slopes is -1, the lines are perpendicular. All right, well, that ordeal is over. We're done. I will post these on Moodle, of course. And now that the dust has settled, we can go back and finally revisit chapter 3. Now, in the beginning of chapter 3, we're going to be looking at imaginary numbers. Imaginary numbers, they're called. Now, we're going to see a video later on today in which it turns out that mathematicians have historically, or at least some of them, found that this is a very poor choice of terminology for these imaginary numbers, because it gives us the idea that they somehow don't exist. But this is the name that we have been using for many, many centuries. So we'll continue to stick with this. But I itself, I mean, this concept of the negative square root of -1. Oh, yeah, it has a lot of potential, that's for sure. I just started playing around with it the other day. And I also stumbled onto another thing that we might be able to use to our advantage in this class. It turns out that Zoom has the ability to create what are called breakout rooms, where you could actually have people split up into groups and working on problems as a team, which I think I'd like to investigate with not just this class, but all my math classes. So maybe not, obviously not today, but maybe as soon as next week, we'll get rolling on something like that, just to see how it works out. Because I think that in a class of this length, the more time you have to practice, the better off you'll be. So I mean, the delta math, I have to get through it again and see exactly how you can use it in your class. But it is a set of practice problems that are already written up. And so it might be possible to use delta math in these breakout rooms and just get more practice in each class. But I have to look into it. I'm not a very big technology person. I'm so far behind the curve, but I will look into this and see how it works out. But I really am excited by the idea, especially of the breakout rooms, because I know other people have told me that it works well. And honestly, it also gives you a chance to kind of meet each other, which right now in this setting is not actually happening. So definitely sometime next week, we'll start doing one of these for sure. Either the breakout rooms or the delta math or some combination of both. But this way, the focus can be more on practicing as we go along, rather than waiting till we're done. So yes, that's where we're going. But again, that'll have to wait till at least next week. But anyway, in the meantime, I was starting to say that these imaginary numbers, now the history of math itself is extremely interesting, because a lot of the concepts that we take for granted, I mean, somebody had to think of them. They didn't just pop out of the sky. Some mathematician or other invented everything that we know and love as the field of math. And so there's a lot of resistance to imaginary numbers. And but of course, at one point in history, there was resistance to zero. There was resistance to negative numbers. There was even resistance to irrational numbers during the early days of ancient Greece. There's a lot of controversy over irrational numbers. So, I mean, these different societies took their math very, very seriously. And so, I mean, it's hard to imagine today controversy erupting over numbers, but it has happened throughout history. And so we're going to watch a video or series of videos which not only explain how these imaginary numbers work, but how they were developed and why. Most importantly, why were they developed? In other words, what was the point? You know, usually the whole idea of numbers is that they were developed because they were useful. Like in other words, even the digits like 1, 2, 3, 4, 5. What are they? What is their purpose? To make things easier. In the early days of the human race, it became clear that we needed a way to keep track of information, even if it was just something as simple as how many chickens do I have, or how many eggs are my chickens laying, and that kind of thing, or how much money does my neighbor owe me. So all these numbers, all these different concepts were really developed to be useful. So you can imagine why it took so long to come up with this concept of square roots of negative numbers, because it's difficult to visualize a real need for them. And yet it turns out that they proved to be extremely useful. So anyway, and then by the way, they're not as scary as they look. It's just that we have to get used to their properties. And I may have mentioned this once before, they're definitely used in engineering applications. And sometimes in statistics as well, you do run into this occasionally. So really what they're ultimately meant to do is help us solve problems. But certain types of equations will generate imaginary results or imaginary solutions, and we just have to deal with them. So we start out by noting that formally, the square root of -1 is defined as this number I, which from now on, all these imaginary numbers will always be expressed as a function of I. So what we need, so for any root, even root, we should say here, of any negative number, we'll end up with an imaginary number. Okay, so let me just quickly mention that when we say the word even root, what are we talking about? For example, the square root, the fourth root, the sixth root, the eighth root, the eighth root of x. These are the so-called even roots. And then we have the so-called odd roots. Okay, so even would mean roots like the square root is the second root, the fourth root, the sixth, the eighth. Those are all even roots. For the odd roots we have on the right-hand side. So the difference between the two is that the odd root of a negative number the odd root of a negative number is a real number. Just as a quick example, the cube root of -8 is -2, but the even root of a negative number is imaginary. Okay, so once you start getting involved with taking even roots of negative numbers, the result is guaranteed to be imaginary. The odd root's not a problem. We don't have an issue there.
But Professor, I just want to
Yes.
make sure that I'm understanding this right. Like, if you do the even root of a negative number, it's imaginary, but it still is like a value, right?
It's an actual value,
It's
yes,
an actual value.
exactly.
We just call it. It's not like it doesn't exist. It's you're gonna get a
That's
number,
right.
but okay, cool.
That's exactly right. Remember, I think I mentioned before, there's some mathematicians throughout history who have objected to calling them imaginary numbers because it gives people the impression that they don't really exist. It's just, well, you'll see in the video that what they try to do is think of it as maybe like a different dimension. In fact, let me show you a quick sketch of that. So yes, the word imaginary should not be interpreted to mean it doesn't really exist. It's kind of an unfortunate choice of terminology, but somebody came up with that name and it's kind of stuck. But it does exist, but we can't directly observe it in practice, but it is a valid number. So one of the videos that I was showing one of my other classes, they tried to explain the way to look at this in the following way. Here's your real number line. And you have all the familiar numbers, 1, 2, 3, and you also have all the irrational numbers, like for example, in here you find radical 2, that kind of thing. So what they're saying is the suggestion is to think of the imaginary numbers as being a different axis, this kind of thing. that this is something that's not directly observed in the real world, but on the other hand, all numbers, when you ultimately come down to it, are abstractions anyway. These are just tools that we've used to help us understand what we're seeing in the real world. So they're saying that it's probably better to think of these as being in a different dimension of their own, separate from the real numbers, but still they're all numbers. I don't know if that helps anybody think about it that way, but you'll see in the videos that they've got some pretty cool graphics to go along with this, I must say, to help us visualize what these numbers actually are all about. But the thing is, the other alternative names that were dreamed up were kind of boring names. Like one of the great mathematicians thought of them that we should call them lateral numbers. I don't know. That sounds kind of like, what does that tell me? Lateral numbers. But no, the name didn't stick. And so we still call them imaginary numbers, even though they're not really, obviously they're not imaginary. They're not, let's say, like unicorns, which are beautiful, but they don't really exist. These are very bizarre numbers, but they do exist. And we can prove it too. Based on the rules of math that we've agreed on, they do exist. And then keep in mind too, and again, you'll see this in the video, somebody had to come up with these other ideas. Like, you would think that, these are very natural ideas, but it took until about the 9th century before Western Europe accepted the idea of zero. And you can imagine how much resistance and negative numbers met up with when they were first introduced. But somebody had to come up with these ideas. And so the imaginary numbers are basically in the same boat. In fact, they were very important. It turned out they were very important in the development of math history, because before they were discovered or created, there was a lot of important equations that couldn't be solved. And so, some mathematicians really focused their attention a lot on theory, and they were the ones who came up with these ideas. Other mathematicians are more interested in practical applications. And for them, this might have been something they would have stepped around, but yeah, certainly they do exist, and they do come up in certain situations. Like, let me show you a quick example of this, which you'll see in the video. Note, for example, that if we have a quadratic equation, let's say we have something like this: y equals x squared minus let's say it's something like this. And this is a parabola, of course. And let's say the solutions would be, it would look like this. This is a rough sketch. Over here, you would have -1, 0. And over here, you'd have +4, 0. Now, how do you know that? Because these are the 2 points, these are the 2 values of x where this function equals 0. Okay, in other words, where the function crosses the horizontal axis is where y equals 0. So you can prove this by showing that. Let's rewrite this as f of x. F of -1 equals 1 plus 3 minus 4. Okay, so that one works. How about f of 4? This equals 4 squared minus 3 times 4 minus 4. 16 minus 12 minus 4. Okay, so this is a parabola. It's a quadratic equation, and it has 2 solutions. And that simply means that's where they cross the horizontal axis. On the other hand, let's look at something like this. Now, this one has a problem. It never crosses the horizontal axis. And yet, if you look at this, if you set this equal to 0 to look for the solutions to this equation, oh my God, the solutions are plus and minus I. Oh no, now what do we do? We're in trouble, aren't we? Because in the early days of math, I didn't exist. And so people felt like, well, then there is no solution. But one of the great mathematicians of all time, Carl Gauss, came along and said, no. He basically told us that for any polynomial, the number of solutions equals the highest power in the polynomial. In other words, in this case, that would be 2. So we're guaranteed the existence of 2 solutions, real or imaginary. Okay, so in other words, he's basically saying, yes, they do exist. We know, and the proof is beyond the scope of this class, but the proof is that he's saying no matter what the highest power is, that tells me how many solutions there are, but that includes potentially both real and imaginary solutions. So in a case like this, the solutions are imaginary. And now you can't, it's hard for me, it would be impossible for me to draw this properly, but you would have to imagine that the solutions are not here, but if you can visualize my pen coming off that slide towards me, that would form a new dimension along which I would find those solutions. Don't worry about that part of it. The videos will show you exactly what that's all about. It'll help you visualize what imaginary numbers actually should look like. But you can see the dilemma here. And this is why, mathematicians thought, oh no, what do we do? We've got a paradox on our hands. We know that there has to be 2 solutions, and yet we can't find them until they started to say, maybe there do exist these other numbers, which we'll call imaginary numbers. And so somebody had to come up with this idea, which happened, God, what year? We're looking, I think, now at maybe the 16th, 17th centuries. This is going back quite a ways, but not as far as the rest of the real number system. Like I said before, 0 wasn't really accepted in Western Europe till about the 9th century, if I remember correctly, because the Romans didn't like the idea of 0. They thought it didn't belong in the number system. So they were part of the reason why 0 took so long to be accepted. But anyway, let's get back to this for a minute. So now the terminology changes slightly when we combine real and imaginary numbers. We often hear them referred to as complex numbers. So in other words, if I start with I and I multiply it by 3, which is clearly a real number, and add another real number to it, or anything for that matter, AI plus B is defined as, or we're going to call it now, a complex number, which means that it is a mixture of an imaginary number and real numbers. Okay, so you can think of complex and imaginary as basically the same idea. All right, now as it turns out, we can actually perform algebraic operations on these complex numbers, although the rules might surprise you from time to time. We get some very strange results. We can get very strange results. Okay, so in particular, when we multiply them together, you might be surprised to see what happens. As far as addition and subtraction goes, let's say you had something like this, 3i plus 7, and you wanted to add it to, let's say, 4i plus 8. Well, it's pretty clear that you end up with 7i plus 15, so there's no problem there. But when it comes to multiplication, the results will occasionally surprise you. Okay. So now clearly, if I equals negative square root of negative 1, it stands to reason that I squared is negative 1. And that's exactly correct. Now, that means that I cubed, which is simply I squared times I, must be negative 1 times I, or negative I. So I cubed reduces to negative I. And then I to the fourth, which is I squared squared, is negative 1 times itself, or just 1. Ooh, now, what happens if I take this one step further to I to the fifth? That would be I to the fourth times I. It's just equal to I. And so basically what's happening is that as we go through these exponents, we're going through a cycle which repeats over and over and over again. There's only, the first 4 are repeated over and over and over again. All right, so let me show you, let's see if I can consolidate these somewhere. So remember, let's repeat all this. We have I to the first equals I squared is negative 1, I cubed is positive 1. No, it's not. Sorry, it's negative I. What am I saying? I to the fourth is positive 1. And then if you look at these carefully, then we start all over again. I to the fifth is I to the first. I to the sixth is simply I squared. I to the seventh is I to the third power. Yes. Oh, really? Is it not working? That's weird. Sorry about that. I didn't know anything was going wrong. It's not telling me that there's a problem. But yeah, if you missed something important, you know, these are all being recorded and they're all going onto my YouTube page, which even though I'm not Mr. Technology by any means, I at least was able to figure out how to put the videos on YouTube. Oh, okay. All right, good. Well, that's unfortunately, I guess it's possible for individuals to have problems with it. Oh, no, don't worry about that. It keeps track of everybody who's here and when they log out. It wouldn't count as being logged out because it's just a connection problem. You're good. Don't worry about it. All right. Anyway, so this one is I3. I cubed is the same as I cubed, and this one is I to the fourth. So you can see we just continuously go through this cycle over and over and over again. All right. So in other words, if you were I9 would be I1, I to the 10th would be I squared, I to the 11th would be I cubed, and I to the 12th would be I to the 4th. And again, it just keeps going through the cycle over and over and over again.
Hey, Professor, I just have a quick question.
Yes.
So you said like I to the 8th is equal to I to the 4th, but then I think I remember you saying also that I to the 4th is equal to 1.
It is, yes.
And so you could just say I to the 8th equals 1 then, right?
Yes, you could, yes.
Okay,
but I just wanted to show you, that's absolutely true. I just wanted you to see, though, that it goes through this cycle.
Yeah.
Okay, so you can tell already. Now, again, like I to the 13th would be I to the first. I to the 14th would be I squared, et cetera, et cetera. But yes, you're right. I to the 8th is 1, and so is I to the 4th.
Okay, cool. Thanks, Professor.
Okay. So this way, I don't know. I mean, I thought you'd find this interesting, but it helps you keep track. Now, we're not going to be running into I to the 16th power, for God's sake, but it's interesting to note how these are related to each other. All right, now, here's an interesting, we're going to start now by looking at algebra on these imaginary numbers. And here's an important definition. You'll see it'll come in handy later on. If you have two complex numbers, let's say you have a plus bi, then A minus BI is defined as what we're going to call the complex conjugate of the first number. In other words, the complex conjugate of this value is this one. Or you could think of them as being complex conjugates of each other. Because they're the same thing except one is positive and one is negative. So we'll save this one. When we get, there's going to come a point when this is going to come in handy. So just for now, let's just note this terminology. When you see these words again, complex conjugate, you know what they're referring to. And then we'll see that, like I mentioned before, adding and subtracting complex numbers is easy. It couldn't be any easier. You just have to organize them properly. Okay, so let me just show you the rules. And you'll agree with me, oh, this is easy. What's the problem? There's no problem there. So you're basically consolidating the constants here. And of course, these are the coefficients of I. And the same thing holds with subtraction. Okay. Now that looks very bizarre and abstract, but let's just look at a couple of actual examples and you'll see that it's not hard at all. All right, let's look at some examples and you'll say, now let's add and subtract these two. Well, I don't think we'll have a problem doing that. In fact, what you could do is you could actually line them up if you really are concerned about it, making mistakes. You can see this is negative 3i and this is 7. And if you want to subtract them, you could actually rewrite this as 3 plus 4i, and down here you have minus 4 plus 7i, and you've got negative 1 plus 11i. Or you could just line them up and just add these and these, or subtract as the case may be. All right, it's up to you, but either way, you can see all we're doing is combining the like terms, I guess you could call them, the constants, and those get added or subtracted, and then the coefficients of I. All right, so let me jump ahead to the next page and show you how it was done here. So here we just literally added the 3 and the 4 together to come up with that 7. And then for the I, we just combine these two, 4 and negative 7, leaves us with negative 3i. When subtracting, though, we of course have to be careful to distribute the negative sign to both of these terms. So you've actually got, actually, let's do this real fast. Just a quick reminder that what you're actually doing here is this. By distributing this negative sign across, you can see that you're going to wind up with negative 1 plus 11i. So it's just a question of being careful with those pesky negative numbers. All right, is everyone caught up? All right, I'll tell you what. Oh my God, it's 9:45 already. All right, now I owe you a break. So we're going to have our break right now. Now, when we get back, before we get back into this material, I want you to see at least some of this video. Now, the video has been broken up into multiple parts, so we can kind of watch a few of them or some of them. The reason why it might be better to watch it all at once is because it's sort of like, you'd be surprised, but the way he writes this video, the author, it's almost like each one has a cliffhanger at the end where you wonder what's coming next, because he's talking about not just I and its properties, but the history of its development, which you'd be surprised to find out is actually quite interesting. So we'll start to watch the first few sections, and then either we will carry on with the material and save the rest for next week, or we'll just blow through all the videos and have a very intensive experience with complex numbers today, or imaginary numbers. We'll play it by ear a little bit, but whatever happens, when we get back from break, we're going to watch at least a few videos, which I'm sure you will find very interesting. Oh, I'd say, realistically, let's say 15-ish minutes, just enough to get some coffee and some munchies. And I assume you're home and you can run into your kitchen real fast. Yeah, this is a long class. I think we can justify a good solid 15 minutes or so. Okay. And if you're a little late, it's okay. The police are not going to come to your house if you're 2 minutes late coming back from your break. Okay. And of course, if you really do have to go do something else, if like the phone rings and is important or something happens, you can always watch the tape if you miss something. It happens. All right. So I'll see you all in a few minutes. It's 1:15. Let's just aim for 10-ish to come back. And then we'll start watching these really interesting videos. Okay. So, all right. We'll be back in a bit. let's see. So I'm just going to go get those videos. There, here we are. I guess everyone's more or less back. That's right. I'll give everyone a minute to get back. And but as soon as, yeah, what I'm going to do is get this. Now, as usual, when we watch a video, so I'll send it to you by the chat box. And you can watch it on your screen because you won't be able to hear it from the side. And so let me see. Now, each one of these parts is about maybe 4 or 5 minutes long. And so you can see it was done that they, instead of having one long video, it's broken up into quite a few bits, as a matter of fact. But it's quite interesting. It teaches you a lot more about imaginary numbers, but it also gives you a very interesting look at the history of math itself, not just about imaginary numbers. So I think it's definitely worth a while to check this out. So first, let me put this first one in the chat box. And let's take it from there. All right, so here it is. So why don't we check this one out? And when we're done, we'll come back and discuss it a little, and then we'll look at the next piece.
This pair of glasses right here, and I really haven't taken it off.
All right, are we all done? Okay, good. So far, so did you like that graph where they showed you how they pulled another dimension off the graph into the air, basically to show you where the that parabola actually crosses the x-axis, not on the flat plane that we're used to seeing, but in another dimension, which is meant to represent the imaginary numbers. So it's a kind of an interesting idea that the imaginary numbers actually are found in a different dimension. And that's what was required to come up with this idea. But you can see it is important because otherwise, without those imaginary numbers, it violates one of the principal fundamentals of math, the so-called fundamental theorem of algebra, that we know how many roots a polynomial has by the highest order in that equation. So he showed us an example of one that would have had no solutions without imaginary numbers, even though we know perfectly well that it must have two. So yes, they were created along the centuries, just like zero, which again met with a lot of resistance. And so did, of course, the negative numbers, but eventually they came to be accepted as perfectly valid numbers. And then, of course, then along come the imaginary numbers. And so they also met with a lot of resistance and still do to this day, but they're all accepted as real, actual numbers, not just a figment of our imagination. So now we're going to be looking a little bit more at the history of how it was they were determined or discovered. Yeah, the thing is, a lot of people would question whether we should say that they were discovered or invented. But so we're going to look at part 2 now, which is a little bit more about the history of the imaginary numbers. Let's take a look at this one. All right, let's check it out. All right, are we ready for part 3? Yes, we are. You will not, if we don't see the part 3, you'll be wondering all week what's going on with this Cardan. So we're going to watch part 3 now. We'll learn a little bit more about the history of math. You can see though why this was a problem, because we have pretty straightforward cubic equations that seem to be without a solution, which we know it must exist. So what do? All right, let's find out. Here we go. So this is part 3. Let's check it out. All right. All right. So I guess let's check out part 4 now in this ever deepening mystery. There should be a TV series about mysteries of math. Boy, they'd probably get a lot of viewers on that one. We'd watch it, that's for sure. All right. So there's number 4. Ooh, we can't leave that one hanging. All right. Well, that was an interesting point. What exactly is, how can we have a negative area? Oh no, we're in trouble again. And poor Bombelli had no idea what he discovered was so important. And well, that's why nobody's ever heard of his name before until we watched this video, because he should have written a series of papers about it, and he would have been one of the most famous mathematicians in Europe. And yet he said, nah, this isn't really that important. Nah, what the heck, you know? And that's so sad. All right. So, but we on the inside, we know who he is. We know Bombelli's name. So, all right, let me send you part 5. I can't leave you hanging now. You've got to know what comes next, don't you? That's right. It's the plot thickens. All right, so here comes part 5. All right, let's check it out.
Left off.
Oh my God. It's getting cooler all the time. In fact, are you starting to think about changing your major to math just because of that video? That's how cool it was. It's starting to make you think, wow, this stuff is more intense than we ever even realized. And there's a lot more going on behind the scenes to get to the results that we have and take for granted. Man. All right, here we go. Let's what could they do to top that? I don't know, but let's find out. All right, hold on. Let me get it out to you. Okay, here comes part 6.
Last time.
Wow. There's even a website for all this good stuff, which I know you're going to be searching through. As soon as we get done here, but all right, so we're going to find out more about how complex numbers work in part 7, but he's going to do it in a very unique way, which involves other techniques that you've already been exposed to. So why don't we check it out? So this is part 7. And let's check it out.
Last
Wow. All right. I'll give you all a minute to catch up and then we'll start the next part. There's only 2 more parts, sadly enough. And then when we're done, we'll get back to the notes and we'll go back and revisit some of these ideas, especially the multiplication part. Hmm. All right, let's go. Let's see. Here's part 8. Let's look at it. Mhm. All right, so we're almost there. So I do want to point out that unit circle he brought out for a minute. We're going to see it again in chapter 5, which is our discussion about trigonometry. So we'll get another chance to look at that again. But you can see what he's trying to say is that trying to solve those equations algebraically could be a major, major headache. So in those cases, you might be better off switching over to the so-called complex plane, where you can use essentially what amounts to geometry to help us figure out the correct solutions to these equations. And so it's kind of a clever idea, but it does help us understand too why complex numbers have the potential to be so useful, in spite of the fact that, let's face it, you don't see those in the real world, and yet they still have a very, very, very important role to play. All right, here we go. Now, this is the grand finale. It's like the end of a long series like Downton Abbey. You wonder how all the characters are going to turn out. So, all right, here we go. Part 9 is the grand finale. And here we go. right, I think we're all pretty much done. All right, well, how was that? Was that impressive or what? Do we now have an extremely deep appreciation for complex numbers and imaginary numbers? Yes, we do. Very good. I see at least one thumbs up there. That's good. It was very well done, I thought. Very well produced, very clever, interesting, fun, engaging, anything you could ask for. That was it. I don't know how many likes this guy's going to get because of the complexity of the topic. Well, 17,000 people liked it. Well, that's pretty impressive. Sure, go ahead, do that. I will be working on it, but a reminder is always good. All right, anyway, so wow, 17,000 people out there were actually willing to watch this series. That's pretty impressive. That's because people don't generally realize how much good stuff really is on YouTube. We know that there's a lot of pretty terrible stuff on YouTube, but there's also a lot of really good stuff too. So this is a lesson to all of us. Always look at YouTube whenever you want to find something cool, and you never know what you might come across. All right, now let's get back to the properties of complex numbers, which we now have a much deeper appreciation of. So multiplying them out, we follow the distributive rule of multiplication over addition, just like you would with real numbers. And so we're multiplying a times b to come up with this term, and a times ci to come up with this term. Just like now, everybody knows this one. For example, if you came across something like this, 3 times 2 plus x, I mean, you would intuitively know that this equals 6 plus 3x. You may have even forgotten that this property has a name, but it is in fact the distributive property of multiplication over addition. All right. Now let's look at some examples. So we'll multiply 3 times this value, this expression, to come up with 3 times 2, and then we have minus 3 times 4, and so our final result is 6 minus 12i. Perfect. And of course, just like we said before, since I is an imaginary number, although as you know, Carl Gauss would not appreciate us calling it that, this is referred to as a complex number because it's a mixture of both real and imaginary numbers. Okay, so the terminology that we'll use, in spite of what Carl Gauss said, is imaginary and complex. Now, let's multiply complex numbers. Now, oh, okay, look, we have our old friend FOIL. So let's see. Now, this is something that they mentioned in one of the videos. Let's try this. If you have a plus, actually, let's use some real numbers. This is going to be kind of a problem. Let's just make up an example right now. 3 plus 4i will be multiplied by 2 plus, let's say, 6i. So we can use FOIL here, just like we always do, with any binomial expressions that are multiplied together. So f, or first, is here. O would be these two. 18i, that is. Here we have inner, 8i. And then last is 24i squared. So we end up with 6 plus 26i plus 24i squared. But you recall from before that since I is the square root of -1, I squared is just -1. So you've actually got 6 plus 26i plus 24 times -1. 6 plus 26i minus 24. And by the time we're done, we end up with minus 18 plus 26i. Well, so that was pretty straightforward. But again, it helps that we can simplify our results with these different powers of I. And so often we'll end up with much simpler results than we would get with real numbers when we multiply them together. All right. So let's look at some more examples. How about, let's say, these two. Now, I'll tell you what, why don't you take out a piece of paper and you tell me what this product is equal to? All right, I'm going to hide that so you can't see it. What is the product of those two expressions? All right, I think you should be ready by now. So we're going to use FOIL. So let me write out all, oh, you got it. Oh, let's see, somebody did get it. That's right, 13i minus 69, perfect. And how did we get that? Well, let's write out the FOIL this way so you can really see it. So F would be here, minus 6, O is 27i, inner is here, and last would be these two, which is 63i squared. So you consolidate all these into minus 6. These we can add together directly to get 13i. And then here we have plus 63i squared. Now you can convert this into -1. So you'll have minus 6 plus 13i minus 63. And of course, that ends up being minus 69 plus 13i. And we're done. It's that simple. Very nice. All right, now the division you might think is going to be a problem. It is to a point, but there's a strategy we can use to help us do these divisions. I mean, if you look at something like this, it's very possible that you cannot reduce these any further, but there may be opportunities for simplifying, but we have to adopt a very clever strategy. And what is that? Well, let's go back for a second and review a concept that we had earlier, the complex conjugate. All right, so remember how that works. If we have A plus BI, its complex conjugate is A minus BI and vice versa. In other words, they are complex conjugates of each other. Okay, that's what that word means, or that phrase means, complex conjugate. So now, why do we need that? Because let's look at our division. It often turns out that we can simplify these division problems by multiplying our original expression by the ratio of the complex conjugate of the denominator divided by itself, of course, because all of this, of course, just equals 1. We're not affecting our results. Now, why is this helping us? Because look what happens when we multiply these together. If you use FOIL on this setup, you'll see why this might be very helpful. F is A squared. O is minus ABI. I is ABI. And last is B squared I squared. So you're going to wind up with A squared. These will drop out plus B squared I. Sorry, this is B squared I squared. And so this I squared is -1. So look how simple this becomes. A squared minus B squared. And those are both real numbers. So no matter what's going on in the numerator, you're guaranteed to have two real numbers in the denominator. That's why we like this approach. Now, who would think of something like this? I don't know. Somebody dreamed this up. Some clever mathematician came up with this idea that we could simplify the ratio of two complex numbers by multiplying by the ratio of the complex conjugate. And there you go. So let's see how this works. Let's jump ahead and look at a real numerical example. Here we go. So we look at this and say, well, you know, it doesn't look very promising, does it? So why don't we do this? Let's all agree to multiply this by 4 minus 6i over 4 minus 6i. And why don't you take out your paper and work on this for a few minutes and see what you come up with. It might end up being just as messy, but there's a very good chance it could be simpler than what we started out with. And that's really the bottom line. Simplification. In math, at least, we always want to express our results as simply as possible to avoid potential confusion or problems. So let's see what you can come up with. All right, let's see what we did. Oh, somebody's got it. Negative 50i plus 20. Ooh, maybe not. All right, let's find out what happened. Let's take this. And we'll run through it. Of course, it's possible that I've got a typo in my slides too. Let's just confirm this. So you've got, once again, 5 minus 2i, 4 minus 6i, all over 4 plus 6i, and 4 minus 6i. So we'll do FOIL with the numerator. First would be 20. Outer would be minus 30i. Inner is these two, which is minus 8i. And then last would be 12i squared. Okay, so we're going to have 20 minus 38i plus 12i squared, which of course that I squared is -1. So I end up with 8 minus 38i. Now in the denominator, because of the way this thing has been structured, we're guaranteed to get 4 squared minus 6i squared, which means 16 minus 36, which, by the way, let's prove that with FOIL. Hold on one second. Let's apply FOIL to the denominator. So you'll have 16 for F. O is minus 24i. The inner term is positive 24i. And the product here is minus 36i squared. Okay. So we have 16 minus 30. Oh, it's not minus, it's plus. Okay. So yeah, because look what we have here. 16. Yes, that next one looks good. 16 minus 36 times minus 1. 16 plus 36 equals 52. So we should end up with 8 minus 38i over 52. And you can divide all of these. No, I don't think so. 8 minus 38i over 52. Oh, there's a typo in my slides. I have to fix them. Okay, yeah, so it should be 8 minus 38i over 52, it looks like. All right. Right. We have to be careful with this one. You know what? Why don't we do another one just to get some practice? This one I'm completely making up, so I don't know the answer myself. Let's try this one. About 2 plus 3i over 4 minus 7i. Now, this might not reduce to something really nice, but let's try this one using the complex conjugates approach. And let's just see what we can come up with. So yeah, don't forget, what we're going to start out by doing is multiplying this by 4 plus 7i over 4 plus 7i, because these are the complex conjugates of 4 minus 7i. So if you apply FOIL to the numerator, F O inner last all right. That's our numerator. And if we apply FOIL to the denominator, you get first, outer, inner. Last would be, in this case, minus 49 I squared. These always drop out. (16 plus 49), which is 65. Now, I don't think we can divide these out. And so that's the final result. So, the thing is, you might say, well, what was the point of all that work? Well, what we've been able to do is simplify it in the sense that we now have a real number in the denominator instead of a complex number. So a mathematician would say that this is a simpler form, just like when you have radicals. If you have something like this, you usually try not to leave it like this. Mathematicians don't like messy numbers in the denominator. So you would take this one and what we would call rationalizing it, and you'd end up with a very nice result, which is radical 2. It's the same principle. All right. Now, can you evaluate a function with a complex number? Yes. Okay, you saw in the video, we can apply algebraic operations, all the normal algebraic operations apply to complex numbers. So let's try something like this. We start with a traditional, it's a straight ahead quadratic equation, but we want to evaluate it on the complex plane. Let's get adventurous here. And let's say that x equals 8 minus I. Yeah, it would be nice if we could find a way to plot these things out. I guess we could kind of do it. I thought it was kind of intriguing to see all these graphical results with the complex plane. But here we're just going to focus on the algebra. So in other words, what you have to do here is basically replace all the x's with this expression 8 minus I. And in fact, this is golden opportunity for you to practice. So what I'd like you to do is try this and see what you get. Okay, so just replace all the x's with 8 minus I, and let's see what you can do. All right, let's see what we got. Oh, somebody's got the answer. All right, let's see. (180 minus 50i). Ooh, see, I've got 180 minus 46i. Well, let's see. Maybe I've got a typo in here somewhere. So we started out. The tricky one, of course, is this one. 8 minus I squared. Let's just do that separately. So we can write that out as 8 minus I, 8 minus I. And if you apply that to FOIL, F is 64, O is minus 8, I. The inner is also minus 8i. And then at the end here, we have I squared. Plus I squared, sorry. And then this is, okay. So we end up with 63 minus 64i here. Oh, I didn't do it that way here, but all right, let's carry on like this. All right, so let's go back to the beginning. We've got f of 8 minus I is 3 times 8 minus I squared minus 2 times 8 minus I plus 7. So what I'm going to do here is put this expression inside these parentheses. This might be a little quicker than what's going on in the slides, where there's about 1 million steps in progress. So I'll repeat that right here.
Hey, Professor, can you just go over how you got 63 minus 64i for some reason? I thought it was like you would do the negative 8i plus or like minus negative 8i. Not mine.
Oh, that's my fault. I just copied it wrong. So I'm glad you caught that. Yeah, I just copied the wrong thing. And yes, sorry about that. Yes, you're absolutely correct. That was a complete disaster there. It is, in fact, 64 minus 16, not what I stupidly wrote. Okay, yes, that's correct.
Okay, cool. Thanks, Professor.
Much better. Yeah, that helps. Man, you saved me a lot of grief because I would have gotten to the end and gotten the wrong answer. So here we go. Let's try that again. All right. So we have 3 times 63 minus 16i minus 2 times 8 minus I plus 7. So now we can just write out all or do all the multiplications. This is 189 minus 48i. Here we have minus 16 plus 2i plus 7. So let's bring together the like terms. So these constants add up to 180. And then these combined give me negative 46i. All right, perfect. Yeah, so it was a lot of work, and you can see it's easy to make mistakes with something like this, but it did work. All right. Anyway, so I think now let's see what's coming up after this. We got some more examples. And then, okay, then the focus shifts to quadratic functions. Then there's some detailed discussions, maybe a little more detailed than what you're used to seeing with these functions. And then what are we doing in part B? Wow. Then let me go open part B because obviously we haven't gotten into it yet. And we're going to look at polynomials, degrees, long division, and some results. Long division we can actually do with polynomials. All right. So, and by the way, in chapter 4, when we finally get to it, is our discussion about exponential and logarithmic distributions, which these are really, really important in practice. In other words, these will come in handy in a lot of fields like finance and economics and probably biology and some of the other sciences. This is really useful stuff. Now, once all of this discussion is over, at some point, we're going to have to spend one chapter on trig functions, which you probably haven't thought about in a long time, but we will need them. And so somewhere in that chapter, we will go over that unit circle that figured so prominently in the videos, because that's one of the easiest ways to help us remember how to solve for a lot of these trig functions. So there's a lot coming up. Now, I don't remember exactly how the tests are structured, which chapters are the first midterm, which are the second. I'll have to look that up. But in the meantime, here's what we should probably do. Let me go back and grab that. There are actually 2 practice problem sets for chapter 3. I'm not sure if we're ready for either one of them. Let me look. Oh, no, I don't want you to see the answers, do I? We might be ready for practice problem set number 1. Oh, yeah, we are. All right, I'll tell you what. Let's agree to do this one for next time. Number 2, I don't think we're ready for it yet. No, this is what's coming up in the rest of this chapter. So, all right, so here's what our plan will be. For next week, work on chapter 3, problem set number 1. And then, now I don't have any more cool videos for next week. That was pretty amazing, but next week we'll just finish up chapter 3 and maybe start 4, and we'll do the first practice problem set, okay? And then I'll let you know which chapters constitute the first midterm. Whatever that happens to be, we're not just going to say, here's the test. I also will have a set of problems which covers all the chapters that we can work on together to make sure you're truly ready for the first midterm. But I don't expect that to happen for at least a couple more weeks, so you can relax a little. And so in the meantime, just for next time, first, we'll of course read through the slides and make sure you understand what we're doing. But also in particular, let's make sure that we all do the practice problem set number 1 at least for next time. It's all the complex operations that we've been learning. And now we can plow through the rest of chapter 3 and possibly start chapter 4. All right, so by the way, there is a week off in this class. I forgot all about it. Sometime in April, although that's way, way down the road. There's actually a day off. Purchase College decided that, you know what, we lost our spring break, but maybe we should still have an occasional day off anyway. So there's actually 3 days scattered throughout the entire semester. And one of them is a Wednesday, but it doesn't happen until early mid-April. So that week, well, you'll just be off. So in the meantime, and you can see everything we've been doing is right here. We'll just do practice problem set number 1 for this chapter next week, and we'll almost certainly finish chapter 3. It's just a question of how deeply can we get into chapter 4. All right. So that's where we're going. That's our agenda for next week. So if you have no last minute questions, why don't we stop right here, and I'll see you all next time. All right. Oh, I know what's going on. We can't tear ourselves away from this stuff. Can we? No, we can't. You're welcome. All right.
Thanks, Professor.
Yes. See you later. You're welcome.